In this presentation, we're going to consider circular motion, its basic characteristics, and then we're going to look at particular examples of going around curves, unbanked, banked, just right speed, too slow, too fast. That should be pretty interesting. So first of all, circular motion. Here we have a mass M moving in a circle. No gravitational influence right now, just moving around this circle, we'll say at a constant speed. Its position is vector r, right, from the point of origin to that location. That's a position vector. In addition, we have circular motion speed, or centripetal velocity, however you want to say it. Circular motion speed is good. But it is also vector because it is velocity. Then we have acceleration, pointing inward, as you already know from previous knowledge. And the acceleration is radial. It is pointed inward, which is what radial means. Could be outward as well, but in this case it's inward. And that's v squared over r. Also, 4 pi squared r over t squared. These should not be brand new ideas for you. The period, the time it takes to go around the circle once, is the distance it goes divided by the speed, which is 2 pi r over v. All right, so the sum of the forces acting on M is ma, as always, and that is the radial. The a is radial acceleration. So that's m v squared over r. We then have the force associated with circular motion pointing in the same direction as the acceleration. So there it is, F sub c. And what's F sub c? ma sub c, m 4 pi squared r over t squared. Now this is a vector expression for centripetal force, particularly because of this position vector, r. Usually, however, we're just interested in the magnitude of Fc, which is ma sub c, mv squared over r, where v is the speed. And that's also m 4 pi squared r over t squared, just the magnitudes. The first important special case we'll consider is a horizontal circle unbanked. So a car going around a circular track. That is a brand spanking new 2013 model car going around this circle. Isn't that beautiful? And it's got a weight acting straight down, normal force acting straight up, and a friction force. Well, it would have been nice to ask you, what direction do you think that friction force acts? It must act inward to provide the force to keep it from going straight off the road. So that's the direction of Fc. Fc has to be provided by something, and it's friction that provides it. So those are two in the same. Those two forces, really it's just one force, it's friction force. And it's what gives you the centripetal force. So Fc is friction, mu s normal. Now mu s is the coefficient of static friction, and you know what the normal force is. So that's the maximum amount of friction that can be provided. Mu s mg. And so that's mv squared over r. So if you want to know what mu s is, given a particular speed and radius, then the mu s is v squared over gr. That's the size that it has to be. It better be that big. If it's smaller than this, you don't stay on the road. Our next example will consider a horizontal circle, banked. And first we're going to consider that it's the just right speed, namely no friction is needed. So what does that mean? So here we have a choice vehicle here, and this is kind of a cross section of the road. This vehicle is coming at us, but then it's going to be going around and around in a circle here. Hopefully you can perceive that. The picture over here would look the same, but with the tail end of the truck shown. So this is a banked road. Now consider, just make sure we understand. If this was glare ice, and the truck was just sitting here, no friction at all, what would happen to the truck? It's not moving. That's right, it would slide down and go plunk into the inside of the road. Now, by the same token, what if this truck was moving at 470 miles an hour around this bank? All right, you could maybe put some other arguments in there, but basically the answer to the question is, that's right, it would go straight, and as the road banked around, it would not be able to execute the curve, and it would sail off in a straight line, but it would be like going off the outside, the high end of the banked road. The just right speed is when you're just moving at that speed where it just kind of coasts around this thing. It's not tending to slide down nor up because it's going too fast or too slow because it's in slide down. So that's the just right speed. Well, what conditions exist then? What we have is, we have the weight, we have the normal force, and the sum of the forces is sum of the forces in the x, and that's going to be mv squared over r. It's going to be the centripetal force. There's no vertical acceleration or change in positions. This is moving around in a circle, so something has to provide the centripetal force to enable it to go around the circle. So here it is. Notice the size of the normal force compared to the weight. There's a good reason for that. We'll get to in a second. Some of the forces in the x, well, we have theta from the vertical here. Okay, so convince yourself that's the same angle. Now, this horizontal part of the normal force is normal sine of theta, and that is Fc, which is mv squared over r. If we consider the vertical forces, they all cancel. There's no vertical acceleration, so it's 0. Well, we have the vertical part of the normal force and mg that are equal and opposite. So normal cosine of theta is mg. Now let's just divide these two expressions out. So we have n sine of theta over n cosine of theta is mv squared over r over mg. And of course, normals divide out, masses divide out. Sine of theta over cosine of theta is tangent theta, is v squared over rg. So this is the just right bank angle. You want to know what the just right bank angle is? In any situation similar to this, or exactly like this, it's always v squared over rg. This time let's consider the situation where the truck is going even faster. In fact, it's going too fast to stay on this frictionless road. So you better have some friction or it'll go off. Okay, so it's going too fast. You need friction to hold it on. Now think about for a second what direction that friction would have to be. So we have the truck here, and it's going too fast, and it would slide up and off the road if it wasn't for friction. So hopefully you can visualize that the friction now has to be downward or toward the inside of the curve, directed along the line of the bank angle itself, the surface of the road. So here's the truck, we got the weight, we got the normal, and we're moving fast, and this is a horizontal circle still, so the normal is increasing in size. We've got a really big normal force. If it wasn't for this friction force that we're now adding in, we would slide up and off the road. Really straight, but that would effectively go to the outside surface of the road, outside part of the road. And also noting here that here's theta, and we have theta here. And now we also have this, the same angle theta here between the horizontal and friction. This is all important to give a perspective so we can correctly, adequately, completely account for all the forces involved so we don't mess this thing up. So here we go. Normal cosine of theta, normal sine of theta. Now we don't know what the normal is yet, but whatever it is, those are its components. Now you might notice already that this normal, the vertical part of the normal, is now greater than mg. not just equal to mg like the just right bank. That's going to be taken care of from the fact that we have this real force called friction acting this way to make this all come into balance. All right, so the horizontal part of that friction force is F cosine of theta. Notice it's not sine, but it's the cosine part of this. Now that is friction, so that's mu normal, whatever normal is, cosine of theta. Also in the vertical, we have a vertical part of this friction, so that's friction sine of theta that gets tagged on here. So that's mu normal sine of theta. So now we have all the forces broken up into components. Let's take a look at the vector diagram that describes the situation. We have the normal. Hooked onto that we have the friction, the weight, all add together to give us a centripetal force that's pretty large in this case. We're going fast, remember? So we would expect the centripetal force to be pretty good size. So the sum of the forces in the x is F sub c, which is mv squared over r. In the next slide, we're going to show how those forces are both of these, n sine of theta and mu n cosine of theta, comprise the forces in the x direction. Let's solve the equations. Sum of the forces in the x, as I just mentioned, it has both n sine of theta and it's got mu n cosine of theta. So n sine of theta is the part from the normal force. Mu n cosine of theta is that additional little part from the friction force. And that is the centripetal force mv squared over r. In the y direction, they have to add up to 0 because we don't have any vertical acceleration. It's a horizontal trajectory that we're undergoing. All right, so we have 0. So normal cosine of theta is the vertical part. And then we have to subtract off of that the weight, but not just the weight, but additionally the vertical part of the friction force, mu n sine of theta. Now let's solve this for the normal force. So when we do that, n cosine of theta minus mu n sine of theta is mg. Let's factor out the normal. Solve for the normal. Now let's plug it in to some of the forces in the x. We have, in the first term, normal sine of theta, so it's this thing with a sine theta. There it is, mg sine of theta over cosine of theta minus mu sine of theta. Then we're going to add to that mu normal cosine of theta. So there's mu cosine of theta times mg over cosine of theta minus mu sine of theta, the normal force. All right, so that's the centripetal force. Masses go away, and we have, and factor out the g, we have sine of theta plus mu cosine of theta over cosine of theta minus mu sine of theta is centripetal acceleration. And that is a reasonably detailed assessment of a situation where you have a banked curve and we're going too fast, and analyzing the centripetal acceleration in terms of the other quantities. Now let's do it for the too slow situation as well. So here we go. Friction needed because it's too slow. Well, based on the angle that I chose here, you can almost guess that unless this truck is moving incredibly fast, this angle is so steep that, yeah, it's going to have a strong tendency to slide to the inside of the road surface. So, yes, this is pretty safely a situation where friction is going to be needed to keep it from sliding in. So we have the weight, we have the normal. Look at the normal, it's not so huge this time compared to the weight. In fact, you'll also notice that the vertical part of the normal is not enough to overcome the weight. So if this is all we had, we'd be accelerating downward, wouldn't we? To keep us from doing that, we have a friction force acting upward, and that's going to add to the other vectors to keep things in balance. So here's the angle thetas again, different angles. Same angle, different perspectives. So we have the horizontal part of the normal, n sine of theta, and n cosine of theta, the vertical. So that takes care of the normal. And now the friction, we got friction, which is mu n cosine of theta, mu n sine of theta, and that takes care of that vector. Let's take a look at how these vectors add. So we have normal, we have the friction to the upper left off the tip of the normal, and then weight straight down, giving us the centripetal force. And of course, you'll notice that the difference between this situation before we had the friction force going off here, and then the weight down, and then this whole distance was centripetal force. So this is consistent with too low of a speed and a centripetal force that's, you know, not so big necessarily, because it's a too slow situation. This friction is actually associated with the diminution of the centripetal force, even though it's not necessarily in that logical order. So anyhow, sum of Fx is centripetal force, which is mv squared over r. So now let's analyze this again. So this analysis will be almost identical to the too fast situation, so I'll go rather quickly. Sum of the forces in the x, normal sine theta, minus mu n cosine of theta, not plus as in last time. So that's the fundamental difference. So that's the centripetal force. In the y direction, 0 is normal cosine of theta, minus mg, and plus mu n sine of theta. All right, so just a couple minus signs change there will affect things quite a bit. So solving for n, normal cosine plus mu n sine of theta is mg. Factor out the normal, solve for it. Notice the plus sign. Plug in a sum of fx. So we have mg sine of theta over cosine plus mu sine minus mu mg, mu, cosine of theta, and then the denominator. That was unnecessary, wasn't it? Okay, so that's mv squared over r. And this simplifies down again, and we get this expression. Very similar to before, except for the signs involved, and that makes a big difference. So that is a good introduction to some important special cases for circular motion and bank curves.